Beyond fighter jets, India is building a new family of engines for missiles and drones. No turbine, no compressor blades, no moving parts inside the combustion chamber at all. Just a shock wave spinning around a ring, detonating fuel thousands of times a second, and that explosion is what pushes the engine forward. That fired on the testing rig in India, and with it, this country just stepped onto one of the smallest clubs on earth. Here's what was built, why it matters, and what it still has not proven. DRDO's gas turbine research establishment has built a small jet engine weighing about 350 kilograms. Light enough to strap onto a missile, cheap enough that losing it doesn't matter, because it's built to fly once and finish the job. Think of it as a jet engine stripped down, disposable cousin. It's in the same weight class as the engine powering America's Tomahawk cruise missiles and India's own long-range cruise missiles run on something almost identical. India is not inventing this category, it's mastering one the world already trusts. Now put that engine on the battlefield. The army has ordered 106 units of a jet-powered loitering munition, essentially an armed drone that circles the target area, waits and strikes with pinpoint accuracy, landing within 5 meters of where it's aimed, because it runs on a jet engine instead of a propeller, like most drones. It flies much faster than the slow propeller-driven Shahed and Giran drones seen over Ukraine. Faster means harder to shoot down, and it can reach targets deeper inside enemy territory. This is the foundation. Everything that follows is built on top of it. Private firm D-Propulse has demonstrated a rotating detonation engine, and here's the simplest way to picture it. A normal jet engine burns fuel the way a candle burns wax. Steady, controlled, continuous. This new engine does not burn fuel, it detonates it. Small controlled explosions race around a circular chamber, one after another, thousands of times every second, chasing each other in a loop. That spinning ring of explosions is what pushes the engine forward instead of a burning flame. Why does this matter? Because explosions release energy far more efficiently than steady burning does. So in theory, you get more thrust from less fuel in a smaller, lighter engine. For years, engineers worldwide could only get this technology to work in tiny bursts, producing a small fraction of the power a real weapon would need, and often only for a few seconds. India didn't creep up slowly, it jumped straight to a meaningful, higher power output, sustained for a real duration on a proper test facility. And did it as an air-breathing engine, meaning it pulls in oxygen from the atmosphere like a jet, rather than carrying its own oxygen like a rocket does. Most of the world's public demonstrations have stuck to the rocket version, which is the easier problem to solve. The problem has also cleared an important checkpoint. It is no longer just a lab curiosity sitting on a bench. It's been tested in a setup that mimics real operating conditions. The application is obvious: missiles that fly faster than the speed of sound. This power range fits neatly into tactical missiles carrying warheads roughly the weight of a motorcycle, and detonation propulsion could make them smaller, faster, cheaper to build. Further out, the same idea could replace stages in rockets that launch satellites, power drones that fly at extreme altitude, or even feed hybrid engines that combine a normal jet with a detonation booster. But here's the catch. This test happened on the ground on a fixed rig, with fuel and air fed and under perfectly controlled, ideal conditions. That's nothing like what happens in the sky. In real flight, air doesn't flow in smoothly. It hits the engine at odd angles, pressure swings unpredictably, and the whole airframe shakes violently. None of that stress was the part of this test. The single hardest problem still ahead is something engineers call an unstart. Imagine air trying to rush into the engine but getting violently pushed back out, like blowing into a pipe that's blocked at the other end. It can stall the entire engine mid-flight. On top of that, an engine built on repeated explosions vibrates and shakes far more than a normal jet. And taming that shaking will need serious engineering. The same kind used to keep hypersonic aircraft from rattling themselves apart. So in plain terms, this proves the engine can make real power on the ground. It hasn't yet proven it can survive being fired into the sky. What's left is the hard part. Engineers now need to run this engine over and over across hundreds of thousands of cycles to see how it wears down, because materials that survive a single explosion may crack or weaken after the 1000th one. They need better heat-resistant coatings and cooling methods, because repeated detonations generate punishing heat, and they need to connect this raw engine to everything else a real weapon needs. The guidance system that steers it, the sensors that find the target, tested first in simulations, then on real hardware. None of it is fast, none of it is guaranteed. But stake it against the small jet engines already flying on India's cruise missiles and loitering munitions today. And the picture is clear. This isn't one lucky test in isolation. It's a country building its own engine technology from scratch instead of buying it from someone else, and joining a short list of nations that have taken this explosive engine concept out of the laboratory and turned it into hardware that actually produces real usable power. 5 years or 15, no one knows yet, but the distance between an idea on paper and engine that actually works just got a lot smaller.